There are three main options for buffer exchange, basically changing out the liquid that your protein or other sample is hanging out in. They all start with these. There's dialysis, diafiltration, and desalting columns, or some other form of size exclusion chromatography or gel filtration, we often call it. Each of these has pros and cons, and so what you actually use might depend on those pros and cons, which we'll get into, but they also might depend on what your lab has access to. At the end of the day, you can use pretty much any of these strategies for various applications. And so let's talk a little about how they work and what some of the pros and cons are of each of these. With dialysis and diafiltration, so when we talk about diafiltration, it's basically often we're doing it with spin concentrators. Both of these involve a membrane, and your protein can't go through the membrane, and the little things can go through the membrane. In dialysis, the little things, so those components of your buffer, are going to flow in and out, and you reach this equilibrium between what's in the pouch and what's in the bigger bath that it's in. And with the diafiltration, so with like a spin concentrator, here your protein is staying up in this upper chamber, and the little things are going to get pulled through. You're not reaching an equilibrium here. You're just kind of pulling the small things through. And there are also methods like vacuuming and things like this to help kind of get things to go through the membrane. But that's a one-way street, and so you are concentrating things, and so then you have to resuspend it in the new buffer that you want, concentrate it again, resuspend it, concentrate it, resuspend it, concentrate it. And so you do that like 3 times or so in order to get your buffer exchanged. With dialysis here, because you have this equilibrium that's going to get reached between what's inside the pouch and what's outside the pouch, you need what's out the pouch to be a much bigger volume. So we're talking like 200 to 400 times volume, and then you want to kind of change it out midway. And so say you have 10 mils of sample. Well, 10 times 400, now you're talking about 4 liters of liquid. So dialysis is a pain. It takes hours, and it has a really, really large volume that you need. So those are some of the cons with dialysis. The pros is that it's really cheap, except if your buffer is really expensive. With the spin concentrators, the problem here, or one of the problems, is it does take some time because you've got to spin it down, you've got to concentrate it down, which can take a while. Then you have to resuspend it and concentrate it down again, which can take a while. Plus, your protein might crash out, so it might precipitate when it gets to those high concentrations, and it can kind of aggregate on the membrane. So there are some disadvantages to doing it this way, but that is a way that you can do the buffer exchange, and you use less buffer than if you were to do something like dialysis. Finally, my favorite method, desalting. Well, I mean, it's my favorite for some things. And this has been a real life changer. It's one of the favorite things I got with my startup. It's a big desalting column, and it goes on the FPLC, so the ACTA, and basically it pumps the liquid through, and then the things that were in the buffer, the little small things, get stuck in pores in the beads, in the resin in here, and then your protein can't get into those pores, and so your protein goes around, and then your protein's going to come out, and it's going to come out with whatever was in here already. So you equilibrate the column, you fill all those little pores in the beads with the buffer that you want to exchange into, and now you introduce your protein sample. Your protein sample's in the buffer that you don't want anymore. The components of that buffer, however, are going to get stuck in the beads, the little pores of the resin, as the stuff that was in the pores of the resin, the buffer that you equilibrated it in, the new buffer you want, it's actually going to come out, and it's going to come out with the protein that was coming in, because the protein that comes in can't get into those pores because your protein's too big to get into the pores. Your protein goes around the pores, and it's going to come out with what was in the pores, and what was in the pores was the buffer that you equilibrated the column in. So you equilibrate the column in the buffer you want to exchange into, and then the buffer you want to exchange out of is the components are going to get stuck in here, because you're going to collect your protein from down here in the new buffer. Well, the old buffer components are still trapped up here. And so this is a big one. This can take up to like 15 mils, so it's awesome because you don't have to concentrate it down at all. So you can also do gel filtration, like size exclusion chromatography with a bigger column, but like you would use for doing some sort of purification. But in that case, you actually have to concentrate it down first, and So this way you don't have to concentrate it down as long as you're 15 mils or less. You just run it through here, and then you have it for your further applications. And so then you might need to concentrate it in order to do size exclusion for like preparative size exclusion chromatography or something, if you actually want to separate things by size. This is just going to do a bulk separation, like really tiny things like salts from big things like proteins. And so this is a big column for doing that. There are also smaller columns for doing this. So this is a PD10 column. These are commonly used for proteins. They can be used in like a centrifuge, or they can be just gravity flow. These are going to go a lot slower though than like something like this where you're actually pumping things through. They also have small ones that you can use with like a microcentrifuge, and I use those a lot in grad school to remove dyes and radioactive labeling when I was doing radioactive labeling. Again, these are all kind of these desalting columns are used to remove really small things from bigger things. And so it's not like your traditional size exclusion chromatography where you're trying to resolve things of different sizes, like you're trying to resolve proteins of different sizes. You're not going to be able to do that with the desalting column. Instead, the pores in the beads of the desalting column are so tiny that like no proteins can get in, basically. Whereas with one of those size exclusion columns where you're trying to actually resolve different proteins, like separate them out, there the pores are kind of sized so that all the proteins, or at least most of the proteins in the size range that you want, are going to be able to go through some of the pores, but the smaller ones can go through more of the pores, and the bigger ones can go through fewer of the pores, and so the bigger ones are going to travel through faster. But with these, the pores are so tiny that the salts and stuff are going to have to go through, and the other stuff is going to come around. The salts are ultimately going to come out, but they're going to come out much later than your protein. And so if you equilibrate the column with the new buffer that you want to exchange into, now your protein's going to come out with that stuff, and the stuff that your protein came in with is going to be stuck in here until it would elute later, but you want to collect your protein before it would come out. So this is super duper helpful, and I'm a real fan of desalting, but sometimes it's not what's right for your applications. And so there again is the dialysis, and then there is the ultrafiltration filters, basically the diafiltration. And so with diafiltration, you're basically using some sort of force to force things through a membrane, but you choose the membrane so that your protein or other molecule of interest isn't going to go through that membrane. And so that's true for dialysis, and it's true for diafiltration. And so with both of these, you've got to choose a molecular weight cutoff of your membrane. So the molecular weight cutoff is basically, it says that things that are bigger than that molecular weight cutoff shouldn't be able to go through, whereas things that are smaller than the molecular weight cutoff can go through. And it's kind of a rough estimate, and different molecules, if they have different shapes and things, they might still be able to go through even though their molecular weight is bigger than the molecular weight cutoff. And so typically, to be on the safe side, you choose a molecular weight cutoff that is a third or less than the molecular weight of the sample, like the smallest thing that you want to keep, basically. And so if your protein was 30 kilodaltons, you would choose a 30 divided by 3 is 10 kilodalton membrane. And again, these membranes can be in this dialysis tubing, which you kind of clamp. They can be in these dialysis pouches that you inject your protein into, or they can be in one of these diafiltration devices. And so here it's on a paddle. In some formats you see it in a V. And with those, you've got to choose the molecular weight cutoff. With dialysis, you often are going to just use a really low molecular weight cutoff, and because all you're really trying to get rid of is those salts and things. With these, there's no membrane. It's just these pores in the beads rather than pores in the membrane. But those are kind of your three main options. You've got the dialysis, the diafiltration, so spin concentrators, and the desalting columns. And again, you can use any form of size exclusion chromatography will be able to perform that kind of buffer exchange, but the desalting columns aren't going to require prior. And again, you could do that with other. So you've got those three main methods. You've got the dialysis, the diafiltration, so like the spin concentrators, and the desalting columns. Dialysis and diafiltration, these are both going to involve a membrane, and with dialysis, things can go in and out, so you're doing a diffusion-based method. You have your pouch that your protein's stuck in. The little things are going to flow out, and the new buffer that you're exchanging it into is going to be in a bath that this pouch is in. The things you don't want in your... So you've got those three main methods. You've got the dialysis, the diafiltration, so like spin concentrators, and the desalting columns, or some other form of size exclusion chromatography or gel filtration. With the dialysis and the diafiltration, you've got to choose a membrane. So you've got those three main methods. You've got the dialysis, the diafiltration or spin concentrating, and you've got the... So you've got those three main methods. You've got the dialysis. So you got those three main methods: the dialysis, the diafiltration or use of spin concentrators, and the desalting columns. The dialysis and the diafiltration, here you've got a membrane, whereas with the desalting columns, here you just have kind of these pores in the beads, the little resin. With dialysis, you have your protein in the membrane pouch, and that pouch, and you can either have like tubing that then you kind of clamp off to make a pouch, or you have a kind of made pouch that you inject into. And that pouch is going to be in a big beaker that's going to be filled with the buffer you want to exchange into. The little things are going to go through that membrane in both directions. Dialysis works via diffusion. So you're going to have things flow in and out, in and out, in and out, while your protein's staying put. And the things that were in your solution are going to flow out, and then the things that are in this outer solution are going to flow in. But then you're going to reach an equilibrium where what's in the pouch equals what's out the pouch, except for like your protein and things that can't get through. And so you need to make it so that what's outside the pouch is a much larger volume, so like 200 to 400 times your sample volume, and you've got to then exchange things partway through if you want to really get a good exchange and get rid of everything that is in the pouch. And so we can't ultimately get rid of like every single particle because there's going to be an equilibrium reached, but you can dilute it out and then kind of like dilute it out again. With the diafiltration, so with these ultracentrifuges, here you're concentrating it down. When you're concentrating it down, the old buffer is going to flow out. And now you need to introduce the new buffer. And so once your protein's concentrated, now you're going to kind of resuspend it, fill it up with a new buffer, spin it down again, resuspend it in the new buffer, spin it, resuspend it, spin it, and you want to do that 3 or 4 times in order to get like 90 to 95% of buffer exchange. And the problem here potentially is that your protein might precipitate or basically crash out at these high concentrations. It could aggregate on the membrane, and it could take a while because the concentration can take a while. The concentrating it can take a while, but it's probably still quicker than dialysis. Dialysis we often do like in the cold room overnight. Desalting columns are your fastest option typically, and so they come in multiple sizes. So big ones that you can use with the FPLC, small ones that you can use with kind of like gravity flow or in a like 50 ml conical tube adapter-y thing, and then even tinier ones that you can use for things like nucleotide removal, dye removal, radioactive labeling removal, and that sort of thing. And so again, what you use depends on your purposes as well as what you got.